Hello, my name is Mike Hull, and I am a physics education researcher at the University of Vienna. This poster is representing some recent work conducted by myself and colleagues at Kyoto University and Kyoto International University Academy concerning a teaching approach that is used throughout Japan called Hypothesis Experiment Class, or HEC. This poster in particular will look at a lesson from within HEC called The Radiation Around Us, which is specific to radioactivity and radiation that is sent out from radioactive sources. Physics education researchers have found that students think radioactivity is unnatural, it's dangerous. However, work that I and colleagues at the University of Vienna have been conducting have indicated that student reasoning about radioactivity need not be rigid and robust, intact cognitive structures. Rather, reasoning can change fluidly depending on the context of which question is being asked, for example. So looking at hypothesis experiment class and the lesson, the radiation around us, or TROW for short, the question that naturally comes to my mind, my interest, is one, does TROW expect this kind of fluidity in students regarding radioactivity? And two, if so, does that expectation actually have any effect on students? We went about answering these two research questions with several methods. First, to get at the first question regarding TROW and its expectations, we used textbook analysis, looking at the lesson plans and also observing teachers as they were conducting TROW in the classroom, and also observing students in the classroom. To get at question number two, how students are affected, again, we looked at students in the classroom and interviewed a few high school students at Kyoto International University Academy, where TROW was taught. Our first research question regarding expecting fluidity might be a little vague and hard to understand, but it's helpful if we think what it looks like for curriculum to expect fluidity in general by looking at a few examples. One example is the electron gas model used for circuits by Berde and Wilhelm. Another is the 2D mechanics curriculum by Spatz et al. And both of these are based upon the work of de Sessa, who's famous for his theory of p-prims, or phenomenological primitives, who wrote that we should attend to student ideas and help students build on the best of those ideas. This concept of thinking about student ideas and what can be built upon within those ideas is an example of the pieces model for student understanding, which is held in contrast to the misconceptions model in Scher's HAP paper. Whereas the misconceptions model thinks of student reasoning as being very stable, robust, rigid-like, and needing to be replaced with correct knowledge, the pieces model, on the other hand, thinks of student ideas as being made up of smaller knowledge pieces that don't need to be thrown away because those smaller pieces are not necessarily wrong. Rather, they just need a little bit of help being reshuffled. So to what extent does the radiation around us, or TROW, align with this philosophy? We have found the answer to our first research question to be that TROW respects and encourages fluidity of student reasoning. In general, this isn't something specific to TROW, but in general, HEC, Hypothesis Experiment Class, expects that an individual may simultaneously have multiple ways of thinking about a given situation. A quote from the recently translated HEC book is, "Even students with minimal knowledge of the topic at hand will nonetheless probably have at least some naive ideas regarding the topic. These may not be very logical and may even be an amorphous understanding with fluid interpretations." We can see also that not only in this sort of overarching philosophical sense, but also in the design of the class book, that is the lesson for the radiation around us, that fluidity is being expected by students. Here we see an example of one of the problems in this class book. This is problem number 6, which reads, "Another way that we can separate ourselves from the Earth is by increasing our altitude. This photo shows the radiation measurement made at the base of Tokyo Tower. As you can see, the dose rate was measured to be 0.065 microsieverts per hour. If from here we ascend 140 meters to the observatory of Tokyo Tower, what will the radiation level be? The very first step for any problem in the HEC class books, TROW included, is to make a personal prediction. Students individually select their expectation of A, the radiation will be weaker as the altitude increases, or B, the radiation will be the same regardless of altitude, or C, the radiation will be stronger as the altitude increases. After students have made their individual predictions, a public tally is then carried out, where students raise their hands and say if they voted for A, B, or C. Following this public tally, a discussion then ensues. At this point, students are asked if they would like to share why they chose A, B, or C, and it's during this discussion that student ideas are built upon, but not by the teacher. The teacher gives very little correction here. Very little building is done by the teacher. In fact, the teacher does not correct errors in the reasoning of the students at all, but rather leaves them as they are, waiting for students to accept the new information through a succession of results from experiments that are carefully selected and arranged. But it's through the discussion with classmates and the opportunity to change predictions, to change expectations, that the knowledge is being built and that pieces are being shuffled. During discussion about this prompt, for example, about this problem, one idea that came up is the idea that as you go higher, the radiation level should decrease. So this would be a vote for A, because you're farther from the ground. And students in previous problems had learned that the ground is a source of radiation. This idea that the farther away you go, the weaker it gets, is just the opposite of the idea that the closer to something you are, the stronger something is, which was identified by de Sessa as Ohm's p-prim, this very rough general idea that closer is stronger. Another thing that happens during this discussion for this problem is the idea that humidity in the atmosphere, as you go up higher, will act as a shield. So this would be another argument for why the radiation should be weaker. This could be classified as an example of interference, which again is a phenomenological primitive or p-prim identified by de Sessa that we find in any kind of everyday experience of, for example, a parent blocking a child from running outside the home. You interfere with what's taking place here. And as the discussion ensues, these small pieces of knowledge get replaced with other small pieces of knowledge. They become bigger or smaller. They become more dominant or less dominant. And student ideas are naturally, organically shifted. After the discussion has finished and all students have changed their prediction if they want to, the experimental results are then disclosed and the next problem is then handed out. One important thing about this is that, as I said here, the teacher is not correcting errors in student reasoning, and in between problems of the class book, very little, if any, explanation is given. The reason for this can be found also in the HEC book, written by Itakura, the founding father of hypothesis experiment class. The student will often spin out a newer interpretation just to incorporate a new fact. And yet the teacher and the textbook, they just conclude, so we can see that these facts lead to such and such. But in cases such as this, Itakura argues, the teacher has brutally forced a theory on the student. In the way that class book is designed and also in the role that the teacher plays during hypothesis experiment class, we see that indeed fluidity of student reasoning is expected. And not only is it expected, it is also respected and encouraged. The work that we have done studying student impressions of the radiation around us is still in a very pilot stage. We have very little data to speak of, but what we have suggests that students can recognize this respect and encouragement from the radiation around us. Several students were interviewed while I was visiting Kyoto to learn about this curricular approach. Two of them are featured here, Glenn and Ai-kun. And at this point of the interview, I was asking them to compare the radiation around us with previous physics instruction that they had had. And this previous physics instruction emphasized memorization for exams. Glenn said that HEC, in contrast to the traditional instruction, asked for student opinions, and there were debates based on those opinions. Glenn thought that was pretty nice because it's good to see as many different points as possible. Sometimes an individual might ignore an important point. When I asked for an example, Glenn referred to this same tower problem and said, when it was about the tower, I made a prediction that it would be weaker as you go up, but some people were thinking it would be stronger because of things like cosmic radiation. Also, there's concrete on the observation deck, and that could affect the outcome also. So in other words, Glenn is talking about all these different points of view, all these different ideas that were coming up during this discussion on the tower prompt. When I interviewed Ayikun also said that he preferred the radiation around us to the previous physics instruction because, as Ayikun said, the process of repeating an experiment to check things that other people consider to be true can make a person enjoy science. Answers that science give us can be disproven by new experimental methods, and being aware of that is necessary for science to develop further. Aikun said that this is an important thing for people to do and was complaining somewhat that many people don't do that. They simply believe that whatever the textbook says is correct. Aikun, though, said that he's not going to fall into that trap. He says, even if someone tells me, believe this answer, I'm going to think to myself, why should I? Why should I have to blindly accept that this human perception of the world is correct? Because science, Aikun went on to say, because science is not the same as brainwashing. So even if people order me to believe, I'm not going to do so. So Aikun, like Glenn, was aware that multiple views, multiple perspectives were present during the lesson. It wasn't about just believing what the textbook says to be correct. Rather, it's about thinking for oneself. And they saw this as being a positive feature. Glenn specified with the tower problem that the ideas that students raised up were not rigidly held. There were multiple perspectives that students would go from one to the other during the discussion. This, by the way, from these two students is consistent with results from a survey that was administered to students regarding HEC in general. Although I don't have time here to discuss these findings, please see our conference proceedings for more detail. So, in conclusion, regarding our first research question, we find that the radiation around us takes into account shifting of student reasoning. It does this by respecting and encouraging many simultaneous ideas. Regarding our second research question, we find that this is not just abstract philosophy of HEC. Rather, it's something that students can notice, and they welcome the safe space that's created in the classroom to be able to have and discuss their own ideas. These are the citations that were referenced for this poster. I will zoom in on this so you can see it a little bit more clearly. Thank you very much for your attention. We welcome your comments and questions.